Hello everyone. In this section we'll talk about power series. So we'll talk about what they are and where they converge at. So we talked previously about Taylor polynomials and how those are used to approximate functions. In general, when you have a series, you have an infinite polynomial, meaning that you can have a bunch of polynomial terms added together that go on forever and ever. You may recall, so one of the ideas is, recall from geometric series, where these things are just numbers, you had the infinite sum, say k equals 0 to infinity, and if all of these things are just powers of some common ratio r, which looks like 1 plus r squared plus r cubed, and this just continues, this is equal to 1 over 1 minus r, and this converges provided our common ratio has an absolute value less than 1. So we can do the same thing with functions, in fact. So a small adjustment, if instead of having a coefficient here, we have we make these r's just x's, you have the same sort of thing. So this infinite polynomial can actually be approximated by just a pretty simplistic rational expression. So this infinite polynomial can actually be approximated by the function 1 over 1 minus x. That is, in fact, just the Taylor series, since it's infinite, of this function y equals 1 over x. And this only makes sense, again, it's only convergent to this infinite polynomial provided the absolute value of x is less than 1. So let's make some terminology, and then we'll go ahead and look at a few properties of these things. So definition, power series has the general form where we have this infinite sum from k equals 0 to infinity of ck times x minus a raised to the k power. So this reminds us of a Taylor polynomial centered at a because of that x minus a form. So again, where a and c sub k are real numbers, and x is the variable. So the ck's you would call the coefficients, and the values where the series converges are called the interval of convergence. So the values for which the series converges are called the interval of convergence. That just means if you would plug those numbers in for x, you would end up with an infinite series, and does that series converge? So that takes us back to the infinite series from earlier lectures. So the radius of convergence is just the distance from the center to the boundary. So if you had some middle point of an interval, the length of the middle point to one of the boundary points is called the radius of convergence. Okay, so there are a few ways that a power series can converge, and we'll talk about finding those convergence, finding how it converges. And again, I hinted at that earlier, that it will involve a use of something similar to the ratio test. So theorem, we have convergence of power series. So a power series, that general form we talked about, just c to the k times x minus a to the k, centered at a, converges in one of three ways. One, it converges absolutely for all x. So if this is the case, we would say the interval of convergence IOC is -infinity to infinity, and the radius of convergence is infinite. We would say capital R is equal to infinity. The radius of that interval is unbounded. 2, we could talk about there is a real number, so there is a real number capital R. So that is again going to be our radius of convergence. Greater than 0. Such that for x minus a, the absolute value of that, less than r, it converges absolutely. And for absolute value x minus a greater than r, it diverges. Notice I didn't say anything about that exact boundary at r. If we're at r, it could either converge or diverge, and you have to just plug in that point and then evaluate that series as we looked at with our several techniques. So 3, you could have it converge only at a. Because if x is equal to a, then basically you just have your initial coefficient, your c sub 0, and everything else just turns into 0. So in this case, the radius of convergence capital R is just equal to 0. Okay, so let's show how we can use the ratio and root test to determine the radius of convergence for some of these power series. So example, find the radius, let's say find R, the radius of convergence, and the IOC, which is the interval of convergence for each power series. So let's say we have the infinite series from k equals 0 to infinity of x to the k over k factorial. So what we do here is we just essentially apply the ratio test. So here we know since it's x to the k, the center's at 0. So the center is a equals 0 since there's no x minus anything. So we can test the series for absolute convergence. The factorial is a hint to use the ratio test. So using the ratio test, what do we get? Well, that's going to be our little r. This is equal to the limit as k goes to infinity of the absolute value of x to the k plus 1 over k plus 1 factorial times the reciprocal of that, which is k factorial over x to the k. So what do we get? Well, we want to pull the absolute value of x out. So, sorry. This is going to equal the absolute value of x. Again, the limit only involves k, so we can take that absolute value of x out. And this will be the limit as k goes to infinity of 1 over k plus 1. The k factorials cancel out, and you just have that extra term in the bottom. So in this case, that limit's going to 0, so in this case we see that the interval of convergence and the radio, okay, so we get r equals 0. So what does that mean here? So since r equals 0 for all real numbers x, that means the series converges absolutely for all x. So the IOC is negative infinity to infinity, and capital R is equal to infinity. So the radius of convergence is infinity. So one thing to keep in mind here is basically the relationship between, so note, basically your little r is equal to 1 over capital R. So they're kind of like reciprocals. So since your little r was 0, basically the only way 1 over that capital R is going to be 0 is if that is going to infinity. So that's why we distinguish those two things. So don't try not to confuse them. So let's go ahead and try another. So example, let's go ahead and use the ratio test to find the interval of convergence for series k equals 1 to infinity of x minus 2 raised to the k over the square root of k. So again, this one is, so we're still going to be using the ratio test, but here we're centered at 2. So keep that in mind. So this power series is centered at 2. So our little r is equal to the limit as k goes to infinity of x minus 2 to the k plus 1 over the square root of k plus 1 times, and again, actually all these things are in absolute values. I'm often a bit lazy about that if it doesn't look like it's going to be too pertinent. So we have x minus 2 to the k. So what are we going to get? Well, the x minus 2's are going to cancel, so we're going to get that absolute value of x minus 2 in front, and then we have the limit as k goes to infinity of the square root of k over the square root of k plus 1, which just goes to 1. So basically what's going on here, we have r is just equal to the absolute value of x minus 2. So inside this interval, so again, remember this r is like for our series, so this is like a geometric series. So this only converges when the absolute value of r is less than 1. So basically this will converge when negative 1 is less than x minus 2 is less than 1. So if you add 2 to both sides, you end up getting 1 is less than x is less than 3. So that tells us exactly what our radius of convergence is, or our interval of convergence. So here the IOC is 1 to 3, and our capital R, our middle point here would be x equals 2, and 1 is 1 away from 2, and 3 is 1 away from 2. So we say our capital R is equal to 1. So that's it for finding the interval and radius of convergence there. Again, remember that little r is like from the series, and the capital R is talking about the radius of convergence, which is half of the interval of convergence. Okay, so let's look at how we can talk about some power series we know to get other power series. So a lot of times we can combine these things. So let's recall from the beginning again. We had that geometric power series 1 over 1 minus x is the same thing as 1 plus x squared plus x cubed, and so on. And again, this converges for absolute value of x less than 1. So let's find the power series for the following functions. So what's going on here? Well, so this is an example. So I should have normally put example at the top. So let's, my mistake there. So we have example. So the example here, A, let's start with x to the 5th over 1 minus x. So as you can imagine, we can kind of like play games with algebra here the same way we would. So we can write this as x to the 5th times 1 over 1 minus x. And then as you imagine, the power series we get here is just going to be as if we distributed x to the 5th through them. So this is just going to be x to the 5th times 1 plus x squared, and so on. So this gives us our power series of x to the 5th plus x to the 6th plus x to the 7th, and so on. So that's our power series, and it's going to have the same radius of convergence. This is still for the absolute value of x less than 1. Okay, so let's go ahead and do another one. Let's say we have 1 over 1 minus 2x. Well, this kind of looks like our 1 minus x, but with 2x substituted in. So we can do the same thing there. We can actually just replace each of our x's with 2x. So plus 2x squared plus 2x cubed, and so on. And that's how we get our geometric series. So we could try and rewrite that in terms of the series notation if we want, and it's really quite easy. It's just the series from 0 to infinity of 2x raised to the k power. So pretty simple there. What about the radius of convergence here? Well, we made a substitution. Normally it would be absolute value of x less than 1. But here, what we have is the IOC. We have to substitute where x normally is the absolute value of 2x less than 1, which is the same as the absolute value of x less than 1/2. So this one is just going to have a radius of convergence of 1/2. Okay, so what else can we use this for? We can also kind of get away with differentiating and integrating these things. So I'll just give you an example of each one of those. So it goes exactly as you expect. If you have a power series representation for a function, on the interval of convergence, you can exactly differentiate and integrate term by term, which is really nice. So differentiating and integrating. And we're not going to talk too much about the hypotheses here. In fact, Euler used to do all these things quite a bit without worrying about hypotheses, and They can get quite complicated, but basically if you're on the interval of convergence on a power series, it works exactly as you expect. So let's say, example, find the power series for let's say y equals 1 minus x to the negative 2. Okay, well, the thing that we want to do here is note that if you have y is equal to 1 over 1 minus x, then y prime is exactly 1 minus x to the negative second power. So because we have that radius of convergence, so we know the power series and we know the radius of convergence is absolute value of x less than 1, we can figure out exactly what the power series is and what it converges to. So since y is equal also to 1 plus x squared and so on, the power series for y prime would just be taking the derivatives term by term. So the first would be 0, then we'd get 1 plus 2x plus 3x squared plus 4x cubed, and so on. So for which converges for the absolute value of x less than 1. Now, yeah, so that's exactly how you do it. You just differentiate term by term, and you get the power series for that other function. So if you recognize a function as either a derivative or an integral, then you can go ahead and find the power series associated to it. So let's do one last example where we do it for term by term integration. So find the power series for the natural log of 1 minus x. And as you can tell, so note that if you would do the antiderivative of 1 over 1 minus x, this would exactly be not far off, but it would be negative natural log of the absolute value of 1 minus x. And if we're only talking about a radius of convergence where x is strictly less than 1, we know that subtracting these things, the absolute value is actually unnecessary because we know this is only going to be valid for absolute value of x less than 1, so we're never going to have to worry about absolute values there. So what do we do? So we know that typically y equals 1 over 1 minus x would be 1 plus x squared plus x cubed and so on. So if we wanted to do the integral of y dx, this would be just the natural log of 1 minus x. So this would be, the negative natural log of 1 minus x, which would be the antiderivatives of each, x plus x squared over 2 plus x cubed, I wrote a times there, plus x cubed over 3 plus x to the 4th over 4, and so on. And this continues ad infinitum. And we even actually should have a plus a constant for our constant of integration. So notice, since we actually want to find the natural log, we asked about the natural log. So the natural log of 1 minus x would just have the power series. We would have to multiply everything by a negative. sorry, so there should be all negatives in front because we needed to multiply everything by a negative. So that would be our power series based on that. So that is how you can use that power series to generate some other ones. And the same tricks work for other power series, whether it's substituting, multiplying, or differentiating or integrating. So that's how we can find quite a few power series. So this is Dr. Lennon signing off.